So you're back. I get it. You need a little more help with the double replacement net ionic reactions. Well, that's understandable because it's early in this endeavor. And so we are going to pick up where we left off with lucky number 13. Probably going to go about 20 or so questions, I guess they're questions on this set, and then make a second or third rather recording. So this is the second recording. You're going to be lost if you haven't listened to the first recording where it was outlined as to what the solubility rules were and how this whole process worked. So let's just dive in and get at it. Equal volumes of dilute, equal molar solutions of sodium, there's a 1A metal, get rid of that, carbonate, and hydrochloric, that is definitely in my list of 6 strong acids, so replace that with just an H+, are mixed. So as we said in the first recording, think of your old algebra tried and true technique when it comes to factoring and such called FOIL, which is first by the first, outside, inside, last, and it's the outside, inside part of that you already know that we're going to really deal with. So the outsides would have made sodium chloride, which is incredibly soluble, as you well know, and the insides would make an H+ for the acid part plus carbonate. So carbonic acid is what you'd kind of figure. But there's 2 ways to think about this. When you make an acid, you add 1 proton at a time. So you can just stop right here, make that ion, the bicarbonate ion, the hydrogen carbonate ion, grown-ups that can't get along, of course it has to have 2 names, and call it a day, except that you're not balanced at this. Oh, yes, you are. I take that back, because you have a -2 here and a +1 there, so that's a total of -1, and this side has a -1, so you're finished. But if you go on to make carbonic acid, then you're going to run into a little bit more trouble. And you would never write carbonic acid as H2CO3 in this question anyway. In question 4, you would take it and make it H2O plus CO2. So this is actually the better plan. So get in the habit of making your life easier and just taking and putting 1 proton onto the polyatomic ion to make the acid, in this case, polyatomic ion. So that is the bicarbonate ion. It's interesting, that bicarbonate ion, because it can accept a proton and go all the way to carbonic acid, or it can lose that proton and go back to carbonate. So we call that amphiprotic. So just a new vocabulary word for you. Alright, so when we see the word solid, we have a little celebration because we don't have to think about solubility rules. So we simply write the formula for barium peroxide. So barium is in the 2A's, so it has a +2 charge, and peroxide is O2 -2, so there you go. A +2 and a -2, and there's a correct formula. Is added to cold dilute. All right, that means they're trying to keep it as unreactive as possible if you keep it cold, or if you keep it dilute. Sulfuric acid. So that means you're going to have some H+ and some SO4 2-. So let me point out something about this sulfuric acid. If it did not say cold and dilute, and more importantly if it said concentrated, then I would have written it as H2SO4, because back in the stockroom of a chem lab, the jug of concentrated sulfuric acid really is 97% H2SO4 and a mere 3% water. I don't know of any other acid that exists that way. Alright, but they said cold dilute, so all we want is our good buddy, that very familiar precipitate we keep making, which is BaSO4. Very insoluble. It's a classic precipitate. You don't need the down arrow. I just do it for emphasis. And then because you have a peroxide present, you're going to end up making a peroxide of hydrogen, which is your good buddy H2O2. So don't overthink this. It really is that simple. It's also kind of a classic. You'll see it over and over again. So what is the total charge on the left? Oh, wait, first we got to balance by atom right there. And that takes care of my charge as well, doesn't it? Yes, indeed. Now everything's balanced. All right, moving on. Excess hydrochloric acid is added to a solution of potassium sulfite. 1A metal. That means that chloric is out of there, so this is really just H+. So I have H+ added to sulf. Notice it's an ite, not an 8. So that's SO3 2-, not SO4 2-. And what are we going to make? Well, this is one of those that back in the lecture portion of this, you have to just sort of remember. What's going to happen is we're going to form an oxide of sulfur. So this forms an SOX, a SOX, as opposed to an oxygen or an oxide of nitrogen, which is an NOx. which ultimately makes acid rain for us, but that's another lesson. But what we want to do is do not change the oxidation number of the sulfur. So if you add this acid to a dilute solution of potassium sulfite, bubbles are going to form is the basic idea. So we're going to make water because it is a neutralization, but we're also going to make SO2 gas. And the reason I know it's SO2 gas, because there are many other SO gases possible, is I come back over here and I do these oxidation numbers. For the SO3, 2 minus the sulfite polyatomic ion, I need an overall charge of the charge on the ion, which is -2. We know that oxygens, each of those oxygens, are also -2. So that's a total of 3 -2s, so that's a total of -6. So what would one add to a -6 to equal a -2? Well, one would add a +4 to make that algebraically correct. So I know that this is a +4 sulfur in both sides. It's not changing. And so I need 2 -2 oxides to make that work. What else do I need? I need 2 of these. Now, do I have 3 O's on each side? Yes. 1 S on each side? Yes. 2 H's on each side? Yes. And the total charge on the left is this -2 and 2 plus 1s, which is 0, and the total charge on the right is 0. And I am finished. So this one, you just have to give up and memorize. Sometimes you just have to give up and memorize. I'd rather you be able to think your way through them, but on occasion, you get thrown a curve. So we'll make it up to you on the next one. Dilute sulfuric acid. So now it's dilute. That's important. So be thinking about the fact this is a strong acid. It's in your list of 6, which are HCl, HBr, HI, sulfuric, perchloric, and nitric. So sulfuric acid is added to the solution of barium chloride. You ask yourself, usually a spectator unless silver, mercury, or lead is present. They are not. So what's really going to take place here is I'm going to take the SO42- ion and add it to my good buddy barium or strontium. And in either case, I'm going to make a precipitate. And we're going to make our classic BaSO4. In case you're wondering what else is going on, yes, the H plus from sulfuric acid and the chloride ion would get together and make hydrochloric acid, but also that's in your list of strong. So they would fall right back apart into those very ions, H plus and Cl minus. So you do not have to put this, you do not have to put this. It's just good form, but it's not necessary. You can leave it just like it is. Total charge on the left, 0. Total charge on the right, 0. All the atoms are balanced. I don't have any balancing to do there. Know when to walk away. A solution of sodium hydroxide is added to a solution of ammonium chloride. 1A metal. Chloride with no heavy metal bad guy around. No silver, mercury, or lead. So OH minus plus the ammonium ion, and I cannot help you if you do not know your polyatomic ions by now. What are you waiting on? You need to memorize those. So I'm going to make water because the H plus is going to come off of ammonium and make water. And that's going to leave me with a classic stinky ammonia gas that's going to evaporate. So essentially, back in that stockroom, your teacher has a jug of ammonium hydroxide. It is in solution, it is clear, it is colorless, and the minute you open the bottle, you are painfully aware, because the minute you change the pressure in that system, the ammonia gas actually starts bubbling back out, because the way we make ammonium hydroxide is the reverse of this reaction. We bubble ammonia gas through water, bottle it quickly. Sort of like soda pop in a way. We bubble carbon dioxide through a syrupy, sugary solution, and we bottle it right away, so it'll contain that gas and make a fizz. You won't see ammonia bubbling out of this jug when you open it, but oh my, immediately you will be painfully aware, and if you don't do this under a hood, you're going to regret it, because you're going to get your sinuses cleared really quickly. All right. Next, dilute hydrochloric acid. So I'm thinking that chloric, I'm looking, I don't see any heavy metal bad guys. Yep, that chloric's out of there. This is just going to be H+, is added to a solution of, there's a 1A metal, potassium, and carbonate. So it's a repeat. And you know what? I purposely left the repeats in here for 2 reasons. Reason number 1 is authenticity. When we make worksheets and such, we use real, authentic, retired questions. So if this particular question, like the barium sulfates, show up over and over and over and over again, perhaps that means we really want you to know it. So I like to leave them in there so you get that message that repeat over and over. So you walk away with a little sense of what's really important. You come up with an obscure one every once in a while. Yeah, well, I don't know how much effort you want to put into memorizing all of the obscurities. But the things that show up over and over again, you definitely need to make an effort to remember. So is this balanced as written? I do believe it is. Yes, I have a -1 total on the left and a -1 total on the right, so I'm good. If you make carbonic acid, if you go all the way to carbonic acid, then you're going to have to balance that, and that would look like 2 H pluses plus your carbonate ion. Now, you would not stay at H2CO3, you would go directly to water and carbon dioxide. So both of these are correct answers. You just got to remember that you have to balance. And that if you wrote H2CO3, you're not going to get credit for that product. You'll still get credit for the reactants, but not for that product. All right, 19. I'm going to need a little more room there. Gaseous hydrogen sulfide is bubbled. Oh, gaseous, yes. I don't have to worry about solubility rules. I just write down hydrogen sulfide. The sulfide is in the -2 column of the periodic table, so I need 2 plus 1s, so H2S. It is bubbled through a solution, so I do have to worry about solubility rules, of nickel 2 nitrate. Oh, all nitrates are soluble. And so what would we make? Well, the only thing that can happen here is that we release hydrogen. Probably not as hydrogen gas, because if you take H2S, that's really an acid. That's really hydrosulfuric acid. And so it's going to release that as H pluses. So both of those are going to get released as H plus. Both of those H's right there. And that's going to leave us with Ni with a 2 plus charge, because that 2 is my friend and tells me that's a 2 plus charge. And the sulfur has a 2 minus charge as sulfide anyway, so I make NiS as a precipitate. And again, the balancing was taken care of because I did it when I wrote out the equation. But if you didn't, you need to make sure it's balanced. So what's the total charge on the left? +2. What's the total charge on the right? +2. All right, a solution of sodium sulfide, candidate for skippage, is added to a solution of zinc nitrate. Well, what do you know? S2 minus plus Zn. Now, what's the charge on zinc? Well, you're supposed to know some things, and from that periodic table, you're supposed to know that everything in the transition metals has a Roman numeral except silver, cadmium, and zinc. And if you put those in alphabetical order by symbol, silver, cadmium, and zinc, the first one's a +1 and the other 2 are +2s, the last 2 are +2s. So I know that that is a +2 because I know that little trend, and you should as well. Should have learned that in first year. So we make that precipitate. Total charge on the left, 0. Total charge on the right, 0. No balancing to do. Not too bad. Concentrated hydrochloric acid is added to solid manganese 2 sulfide. Okay, solid. So I'm wondering about that chloride. It would be manganese chloride, and all chlorides, yeah, I can get rid of that chloride. Just make it H+. So I'm going to have H+, plus, I don't have to worry about solubility rule, just write the correct formula for Mn. Again, with the idea, this is a 2+, sulfide is sitting right under oxygen in that column, so it's going to be a -2. So MnS is a correct formula. And we're going to have a replacement going on here. So we're going to have that the H+ is going to bump, and that's going to be a gas. It wouldn't be necessary that you knew that. I just would like for you to know that. It's a stinky gas. It's the rotten egg smell. You know that smell. It's kind of disgusting. All right, so to balance, we must have 2 of these, and so total charge on the left is +2. Total charge on the right is +2. Solutions of tripotassium phosphate and zinc nitrate are mixed. Look at that 1A, get it out of there. Look at that nitrate, get it out of there. Now what do we have? Phosphate. You must know your phosphate. And again with the zinc, and the fact that you should know that zinc is a 2 plus. Plus a Z kind of looks like a 2. Kind of helps you remember it. And what are we going to make? Well, it's a 2-3 trick, isn't it? We got to have 3 of the 2s and 2 of the 3s to go to 6. So we're going to take 3 of the 2s and 2 of the 3s. And to balance it, we still need 2 of the 3s and 3 of the 2s. so that we have -6 and +6. So we have 0 on the left as a charge and 0 on the right as a charge, and we are balanced. I'm a fan of the law of conservation of charge. It makes my balancing life easier. It makes my blood pressure go down to know that I got it right. Dilute acetic acid. Okay, is that in your list of 6? When you see the word acid, you go, HCl, HBr, HI, nitric, sulfuric, perchloric. Nope. So I write it as its formula. An H in front of the acetate ion, because ic acids come from 8 ions. C2H3O2. And there are other ways to write this. I'm not an organic chemist, I'm an inorganic chemist, so this is my favorite way to write it, but you can also write it in many other ways, as you'll see when we do the acid-base chapter. So if you know a different way to write it, as long as you have the same number of H's, C's, and O's, that's fine by me. It's added to solid. Celebrate the fact you don't have to even think about this, just write down the formula. Mg and CO3. Carbonate is CO3 2-, magnesium is sitting in the 2+ column, the 2A column, which means its most likely oxidation state is 2+. So if I'm going to take acid and put it onto a solid carbonate, you need to think about these carbonates in terms of like chalk. Real chalk is calcium carbonate. Well, magnesium is one of calcium's cousins. They're both in the 2A family. So when you take acid and you put it onto like a good old-fashioned piece of chalk, and I realize you don't have chalk in classrooms much anymore, maybe think sidewalk chalk, then you get fizzing, you get bubbles. And so what's going to happen is that you're going to dissolve basically this chalk, and you're going to get the magnesium to free up, you're going to get the acetate, and you're going to make the bicarbonate ion. Now you can make carbon dioxide and water. If you go all the way to H2CO3, I need a charge on that, H2CO3, then your products are going to be CO2 and water, and you're going to have to balance. Alright, so it's just simpler to keep it this way and see if we can get this balanced as is. So what are we going to do to balance this? Let's see. Do we have to do anything? I got my 1H, I got my 1H, I got my 1 acetate, I got my 1 acetate, I got my 1 carbonate, and I got my 1 magnesium. So there we have it. Now the truth is I need 2 here, 2 here, and 2 here because of charge. Because when I look over here and I see just the +2, I need it to be 0 on both sides. And the only way to make that happen, singular, happen, is to double the bicarbonate ion, which forces me to also double the acetate. And I've got a problem here, don't I? Maybe this is a case of when it's easier to go to... No, it's not. I take that back. No, it's not. Do I have this charge right? Yes, I do. Oh, I'm a doofus. I am a doofus. That's what's going on here. I'm missing the charge right there. So let me take that away, and that away, and that away, and try again. Please forgive. I got to talking and didn't put my charge on the acetate ion. Alright, so now I've got 0 on the left and 0 on the right, and everything's balanced by atom, and that's a much prettier picture. So see, that balancing by charge thing, that can be your friend, no matter what your age, because it helped me catch my mistake. Alright, moving on. Gaseous hydrofluoric acid. Gaseous, you don't even have to think about it. Plus, you should know HF is not in your list of 6 anyway, and it's weak, but gaseous means just write HF, because the ic and the hydro. Hydro is a prefix on the acid that says caution, element approaching. There is only one exception to that, and that is hydrocyanic acid. Because cyan, the cyanide ion, Cn-, does not have any oxygen in it, so we treat it the same way. So usually it's an element. So hydrofluoric acid reacts with solid, again I don't have to think too hard, silicon dioxide. Silicon dioxide. So that's an easy point. They gave me that one basically. So what's going to happen? Well, this is a double replacement sort of reaction. So insides, outsides. What would you make? You would make an H and an O together compound. That would be your good buddy water. That's your outsides. And what would you make on the insides? Si. It's sitting in the +4 column right there under carbon. So it's going to be a +4. And then I'm going to put fluoride with it, which is halogen, so it's going to be -1. So I would need 4 of them to write that formula correctly. Now we have some balancing to do. So what are we going to do? Well, I need 4 F's. Oops, it's supposed to be red. Didn't click it hard enough. That's better. All right, so now I have 4 F's, so if I double that, I'll have 4 F's. I had 4 F's, which came along with 4 H's. If I double that, I have 4 H's, 2 O's. I have 2 O's on the left, 1 silicon on each side. I think that's it. And the total charge is 0 and 0, so. But that was where atoms become more important, when it's 0 and 0. Yep, I got it. Number 25. Equimolar amounts of trisodium phosphate, get that sodium out of there, and hydrogen chloride, both in solution. Okay, that's kind of tacky. That means this is hydrochloric acid, but that's okay. We're going to get that Cl minus out of there anyway, but that's really an H plus, not an H. I think that's kind of tacky. Are mixed. So phosphate, an H plus. So just put them together and make a polyatomic ion. There you go. Again, if we kept going with this and we had loads and loads of hydrogen ion, we'd get all the way to phosphoric acid. And if you get all the way to phosphoric acid, that's okay. You leave it as a molecule because it's weak. It's not in your list of 6. And then you balance the equation. So it's okay to do that. I'm just trying to train you to do what's simple that gets you the points. So in reality, these molecules put 1 proton on at a time before the second proton comes on. So just put the first one on there. It makes the math easier, makes the balancing a whole lot easier. Ammonium chloride crystals, yet another word for solid, NH4Cl, don't have to think too hard, added to a solution of sodium hydroxide. Spectator. So ammonium chloride is added to hydroxide. So what's going to happen? This is actually a bit of a neutralization reaction. So anytime ammonium is around, you have to kind of figure if an acid or a base is involved, especially a base in the case of ammonium since it's a weak acid itself, that you're going to make ammonia gas and stinkiness is going to happen. And then the H plus that came off of NH3 is going to become water, H2O, and then Cl minus is the only thing left to be released. So if you made NH4OH, if you left this as NH4OH, you have to realize that that is going to go directly to NH3 and H2O. So carbonic acid and ammonium hydroxide behave that way in an open container. And there was no talk about sealing this or anything like that. So you got to assume an open container. So you really need to get in that habit. So you may have missed it, but that would be why you missed it. All right, where am I going next? Number 27. Hydrogen sulfide gas, H2S, stinky stuff, is bubbled through a solution of lead 2 nitrate. Nitrate's out of there. Lead 2. Well, the logical thing is that the lead 2 is going to take the S and make a precipitate. So that's going to make a solid. And again, you don't have to put that. I just do it for emphasis. And then what? Well, this you should recognize as an acid. So we're not going to release hydrogen gas. We're going to release 2 H pluses. Because when you bubble hydrogen sulfide gas through water, you make hydrosulfuric acid. So you need to start recognizing that in 2 forms. If it's a gas, it's a molecule. If it's a weak acid, it's still just written as a molecule, but you got to remember that it's H plus that you're most likely going to release if you decompose it. Solutions of silver nitrate, let me go to purple. Silver nitrate and sodium chromate are mixed. All right then. Ag plus and CrO4 2 minus are going to make Ag twice CrO4. To balance, I need 2 of those. Total charge on the left, 0. Total charge on the right, 0. Not so painful. Solutions of sodium fluoride and dilute hydrochloric acid are mixed. Sodium fluoride and dilute HCl, hydrochloric acid, so H plus. And we're going to make, let me try that again. We're going to make the weak acid, it's still aqueous, but it's a weak acid, and so we write it molecularly. And we're balanced. Saturated solution of barium hydroxide is mixed with a solution of iron 3 sulfate. What can you do with this? Not a lot. Barium hydroxide, that's weak. How come it's weak? Because oh, I'm sorry, no, that one's strong, so I can disassociate it. It's mixed with a solution of iron 3 sulfate. Sulfate is soluble. So that's all I can do to get started. So barium hydroxide. Again, why am I dissociating that? Because it's strong. How do I know? Because I know that 1 and 2A metal hydroxides are strong, except for the two little guys at the top of the 2A's, and barium is not up there. And then Fe 3+. How do I know it's 3+? That Roman numeral 3 is my friend. Plus SO4 2-. So you got to know your good buddy BaSO4 is involved. And then your question becomes, what about that iron hydroxide business? Most hydroxides are insoluble. And the 1 and 2A metals are the strong that are soluble, except for the two little guys at the top of the 2A's. So we write this as FeOH3. Now, let's talk balancing. I just put a 3 here, so I'm going to need 3 of those. 1 barium, 1 barium, 1 sulfate, 1 sulfate, 1 iron, 3 hydroxides, 3 hydroxides. We're done. All right. Total charge on the left. +2, -3, +3, those two cancel, -2, 0, and 0. All right. That wasn't even too painful. I had originally intended to stop here, but you know what? I think I'm going to push through. No, I'm not. I am going to stop here. I'm going to stop here. That way these are shorter recordings. It won't take up as much room. So we're going to stop here, and we're going to pick up with number 31 in the next segment. So I hope you're finding this useful, but here's what I hope you're not doing. I hope you're not just like writing this down to get your homework done, because that's not going to help you a bit. Because honestly, your teacher isn't going to care about your homework as much as they are the quizzes that they're going to continue to give you all year long. This is the fastest 15 points on the test. Make sure you do a good job. Make sure that you get your average up every time you take one of the quizzes, even if you start with only earning 3 points on a given quiz. Also remember, this is not the format that your quizzes will be in once we kind of get all this stuff mastered. You're going to have to start answering some descriptive questions about it, which is why I tell you some of the descriptive chemistry as we go along, so that you get a feel for some of the chemistry. So I will hopefully see you next time, unless you have gotten so good at this that you don't need my help anymore, which will hurt my feelings a little bit, but I'll get over it quickly. Thanks so much.